Hi, welcome to episode 4. Today we're going to do something a little different than I've been doing for the past 3 episodes, which has been showing off some of my projects. And today we're going to do some educational things. I'm going to be talking about how you can actually sample a signal less than twice its frequency under certain circumstances. So I see this a lot on the internet where people say, if you have some signal of some frequency, if you want to sample it into a computer or into some sort of digital circuitry, you must sample it at a minimum of 2 times the frequency in question. Now, in general, that's a good rule to go by. However, it is actually possible to sample it at less than that 2 times condition. So what we're going to do is we're going to go over to the whiteboard, we're just going to get right into it, and I'm going to show you guys what I'm talking about. Alright, let's get right into it, shall we? So when you have some sort of signal that you want to sample, that signal is made up of at least one, usually many, frequency components that you then want to accurately put into your sampled version of the signal. You don't want to lose any of those frequency components because then you're losing information about the signal. But today what we're going to do is we're going to look at a very special case where you can actually sample at less than 2 times the maximum frequency of the signal. Alright, so let's take, for example, this seemingly random line. So if we were to look at the Fourier spectrum of it, the frequency components that are made up of it, we go over here. Alright, so let's say that this is our condition, right? Let's say that this is what we have. So here I have, just for notation purposes, XC, C is going to be for continuous, and S is going to be for sampled. I should change that over there. Sample. Alright, sorry. So this is going to be our continuous signal, and capital X is going to be for the spectrum, alright? So if we look here, let's say that this is our actual signal in question, not sampled yet, still in the real world, still in, some sort of circuit or something, right? And let's say, let me just go back a little bit there we go. Let's say that the minimum frequency that we're dealing with is 2 pi times 7 radians per second, or 7 hertz, all right? So let's say we have something between 7 hertz and 13 hertz there. So normally, if you were to follow what most people would say, is that you would need to sample this at 13 times 2 hertz, okay? So, or 26 hertz at a minimum. Now what we're going to see is that that's actually not necessary to be able to sample all the information in the signal and accurately reproduce it if you were to then output it back into the real world after sampling it without any loss. So the first step in mathematically establishing a sampled signal is to basically multiply your signal, all right, by a Dirac Comb, all right. So I'm not going to go into what all this means and whatnot and blah blah blah, but each of these little arrows are a Dirac delta function. So basically they go off to infinity, but the area of them is equal to the height of the sample point, blah blah blah. Anyways, not important. This is just another way to represent that, okay? But we're kind of sampled, right? Kind of looks like a sampled signal. And see, I did put an S. So if we go over to the spectrum of it, right? Notice now we have the original part here, 7 hertz, 8, 12, 13, right? But now we've got this component over here, right? So before we go any further, what I've done is sampled it at 14 hertz, all right? 14 hertz, not 26. Okay, so that's the important part. We've sampled it at less than 2 times the highest frequency component, right? So when you sample a signal, what you get in the spectrum of your sampled signal is you get replicas, okay? So replicas oops, I just dropped the eraser, is this right here. This is a replica, see, because this was our original part, right? These parts here, that was our original part, and this is a replica. And if you were to take this graph and you were to expand it out in both directions, you would see that it would continue to repeat. It would repeat itself again and again and again, and in this direction again and again and again, off away until infinity. So, so the thing is that this is a replica. These are frequency components that we do not want. These are lower frequency than these, because everything. So if we're not looking at the additional replicas, because there's going to be replicas every 14 hertz. Okay, that's the other important thing. We sampled at 14 hertz. There's going to be replicas every 14 hertz. So this was the original part that we sampled, right? 0 to 14. So if we take that and we shove it over here, right? Bam. We get our first replica, right? So, you know, this over here, that goes off. That goes off to... is this marker going to work? Oh, apparently not. Okay, hold on. I'm going to go get another marker. All right, we're back with another marker. I'm sorry. So this goes off, ... to, you know, minus... Let's just write that again. Minus 2 pi times 14. And over here, we have 2 pi 14, right? So it's 14 hertz transplanted over there. So if we were going the other direction too, there would be that, copy and paste it over, you know, like just for infinity, as I said. So the frequency components that are closest to your sampling frequency, whether positive or negative, so minus 14 hertz or positive 14 hertz, are the high frequency components, and everything located in between those is the low frequency part. So this here is, you know, going to be 0, but then there's going to be this, you know, replicated again down the line. So those are our low frequency parts. So this here, this part right here, this is low frequency, while the other version over here is high frequency. All right, so that means we want to eventually get rid of that. Well, let's keep going, shall we? So after you've done everything with the Dirac Comb, we're going to go down, and now we have our actual sampled signal. So this is now sample number instead of time, and this is our discrete sampled signal. Okay, so now we're using square brackets to denote that it's a discrete function instead of a continuous function. So these are now, this is now actually what you would have inside your computer, inside your microcontroller, or whatever, right? Inside your memory, where now we have our actual sampled values. You know that this is going to be like 1, and this is going to be like 0.5 or something. You know, whatever. So if we go over here now, back again to the spectrum of this now. So this is the spectrum of what you have inside your computer. This is the important part. This was just like a mathematical construct, right? This is what's inside your computer. What we've got is we've got the same general shape, and I didn't repeat the numbers again over there. Don't worry about that. We have the same general shape as before, right? Where we've got the one part and the replica over here. And we want to eventually get rid of that replica. But first, let's focus over here. What we've got now is, if you were to take the discrete Fourier transform of this signal, right? Of these data points, I should say, of these data points, you would get these values here. And I explicitly wrote everything out without simplifying it. So what we've got, the difference between them is that this here is like real frequency values, and this here is the frequency of your arbitrary data points, okay? And what we've done is we've taken the original frequency and divided it by our sampling frequency. So, you know, you can go through and you can simplify all of them, but the important part is that this ends at 2 pi down here, right? So what you've got now is you've got no information anymore as to what the real frequency is. That's why whenever you take a signal and you sample it and you just straight up do FFT, you don't actually get any real x-axis values. You know, you look at it and you go, well, what's the frequency, right? That's because you haven't specified in the algorithm in your computational algorithm, not in FFT. FFT doesn't actually do this part for you. You haven't specified what the original sampling frequency was. But that's another topic for another time. So you know, you've now got high frequencies located near your sampling here, and you've got low frequencies now located near 0. And yeah, okay, so this of course, you know, goes off just like before, blah, blah, blah. So those are all the negative components. So you want to get rid of those and you want to keep those, and then you want to take these and now put them back into the real world. So how do you now do that, right? Well, that's the simple part. So now you put it back through your digital to analog converter, sampling, you know, going at 14 hertz, okay? Okay, with me so far? You go back out at 14 hertz, and you're going to have an output whose spectrum looks like both of these, right? Both of them. So what we do instead is then you're going to filter out these lower frequency parts by only passing through the high frequency parts, okay? So you want to pass everything above 7 hertz, okay? Remember this is 7 hertz, but you know, it's when you put it back through the digital analog converter, you sample it at 14 hertz, so then you multiply this by 14, so that cancels out. So you can actually sample originally at one frequency and then output back out at a different frequency to scale things up and down, because it's just arbitrary data points once it's inside the digital system. But again, another topic for another time. So you by cutting this off here at 7, right? This is 7. Let's just go back up because I didn't write the numbers here. It's the same thing here though, right? This lower part here is 7, right? Which means that all of that, which is low frequency, will get cut out. Because when you have a high pass filter, what you've got is you've got a pass band that like a frequency spectrum that looks like this, right? And then the mirror on the other side, right? 'Cause the replica on the other side. So that's going to be minus. Oops, actually I should have drawn that on top of that, right? So this is our filter, and this is our filter over here. So those are the parts that we're keeping, and we're filtering out these parts here, right? I'm filtering out up to plus 7 hertz and up to minus 7 hertz, or you know, 2 pi 7 radians per second. Okay, so then what do you get in the output? Well, then you get what you expect, right? You get your original stuff. So that's the 7, the 8, 12, 13, and you've killed everything else that's lower than that. And now you're back into the, so we'll just label that as F. So we're in hertz here, just to label it easier for you guys at home. So then we're back into the original signal. So we've gone from sampling this signal at less than 2 times the maximum frequency down to having it back out at the output without any problems at all. So why is it a problem then in the first place? Let's go take a look, shall we? So this becomes a problem when you have a much more inclusive spectrum than this. So notice how this time we actually have a bunch of frequency components. Oops. We have a whole bunch of frequency components that are located closer towards 0 this time, right? So let's pick an arbitrary number. Let's say that this is, let's just say that this is 14, right? And then this is going to be minus 2 pi 14. All right, so this time we're actually going to have to sample it at twice the maximum frequency here. So let's go through that, shall we? So if you were to sample that and then take a look at the spectrum of it, right? You're gonna have your main one here. So let's say we sampled at 28 hertz, right? So this is our first step, right? So this is gonna be 2 pi 14, 2 pi 14, and then remember, right? We replicate every sample at the sampling frequency, right? So then we're gonna have 2 pi 28, right? Okay, this is obviously not very well to scale, but that's what you get. And then you have another one over there, and it continues on, right? So notice the important part here is that these just come and just touch, all right? The replicas just touch each other. Okay? And there's no overlap. So then what you could do is then you can go and then you can do the next graph where it's then divided by 28. Wow, that's not 28, that's 2 pi. 28, 28, 28. And so then then you get 2 pi, right? So your replicas are every 2 pi in your final sampled one, and that's going to be minus 2 pi. And then notice that this is minus pi, and this is pi, right? Aha, interesting. So when you sample at the quote-unquote, correct frequency, they end up touching at pi and minus pi, huh? And they, replicate every 2 pi. So then you could take that, you could put it back through your digital analog converter, and then filter out the high frequency components, right? Because everything that's close to 2 pi and minus 2 pi, so this is all high frequency, and this is all low frequency, high frequency, right? So what do you have to do? Low pass filter that, low pass filter, and then you would filter out, you would filter that out, and you would filter that out. So, how does this become a problem? Well, let's take a look at that too, shall we? So let's take the same idea that we had before, which was the spectrum that's centered around 0, where we've got something now going to plus 10 hertz and minus 10 hertz, right? Now, normally, so this time, just for clarification, I did change it from 14 to 10, just for illustrative purposes. Normally, you'd have to sample this at 20 hertz in order for the replicas to not touch. But let's say we've sampled it such that they do touch. So obviously we're going to be sampling it at less than 20. So let's say 15. All right, let's take a look. So we've got our chart here, and we go. So this is going to be this is still 2 pi 10 minus 2 pi 10, right? And if we sample at 15 hertz, right, the point at which it, the replicas, the center of the replica, right, because the center of this one's at 0, so we're going to have the same triangle centered around 15. So this is going to be 15 hertz, all right? And we know that it's 10 hertz wide, right? So we come down. And we come down there. So then this is going to be 2 pi 25, and this is 2 pi 5. And then you can do the same thing over there, and blah, 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 blah. I'm not going to bother writing that again. But aha! What happens here? This is the important part. This is why this is a problem. Okay? This here, this is the replicas overlapping each other. That's a problem, okay? So this is some aliasing that we don't want, because if you were to take this now and you were to do the same thing that we did before, the same thing that we talked about, right? Because this is high frequency, this is low frequency, this is our actual signal, high frequency. We want to get rid of these parts, so we have to low pass filter it, right? So if you go if you have two, you have a couple of options for filtering it now. So you can filter it like this, right? Where your original signal had its maximum at. But then what do you get? Well, you're going to get something that looks like this, right? Because that's what you've got here. You've got, this part here you can just basically erase. And you're going to get this shape. You're going to have this high frequency component here that you don't want. Okay, well, what happens if we, instead of there, we we filtered at right in the middle, right? Right in the middle between the two. Well, then you're going to have cut this off instead. Oh, that was bad. Right? So now we're missing some information that we didn't have before. Which, that's another problem. So basically, right here, right, that point is positive 2 pi 7.5, which is, well, half of our sampling frequency, right? So basically, we've cut off, everything from 7.5 to 10 hertz. All that is gone. Well, that's not what we wanted. We wanted to sample the whole signal, right? And we knew that there were some frequency components that are within that frequency range that we wanted. So that's why for these signals you have to sample at least 2 times the maximum frequency that you have. But as we've seen, you don't always have to do that. The previous thing that I showed was it was up to 14 kilohertz, and we sampled at 15, sorry, not kilohertz, no kilohertz, 14 hertz, and we sampled at 15 hertz, and there was no problem. So, lesson learned, you don't actually always have to sample at 2 times the highest frequency component. It's, you got to sit down, you got to take a look at what you're doing. Are those low frequency components necessary? Do they exist? Can we just ignore them? Or what, right? You gotta sit down, look at what you want, and see if you can get away with it. So I hope you enjoyed this little mini lesson that I did on some basic sampling theory. So the problem is that I know that a lot of you are going to be confused with a lot of the notation, and I didn't go into any of the math and all this other stuff, but it's because it took us a while to even get to that point in our digital signal processing class, because there's so much rigorous background necessary to actually fully understand, fully deriving everything and blah, blah, blah. So I tried to skip all that while still showing how, from a practical standpoint, things are important, and what's important and what's not important, and how these things that people commonly say aren't actually necessarily always true, and that there do exist conditions where you don't have to follow those rules while still being able to maintain your signal information. So, maybe in the future I'll go into a little bit more mathematical detail for those that are interested in it. But for now, I think that'll be good for a lot of you guys. I filmed this later in the day here, so I hope this video doesn't come out too dark. But it was the best that I could do with the time today. Anyways, I hope you guys enjoyed the episode. And one last thing before we go. Obviously you remember it, it's only been, 2 episodes ago since the last time we talked about it, my GPIB adapter. I'm going to be releasing it as open source hardware. So I'm almost done packaging up all the files and getting everything all ready. I'm just nearly almost done. Just want to double check a couple things before I release it out. But that should be hopefully either tonight or tomorrow, more than likely tomorrow. And when that's done though, I'm going to also be making it available on the internet for people to purchase from me if they're so inclined. I've been getting a lot of quotes for getting the PCBs done in Canada. You know, would rather not have it sent to China, rather support my fellow Canadians. So yeah, we'll see how things go. Hopefully I can put in a PCB order next week. Anyways, guys, until next time, bye.